Okay, we're 9 o'clock sharp now, and hi everyone. Welcome to today's tutorial, and today I'm going to introduce to you about how to add a new RISC-V extension in Spike. And my name is Eop. I'm a compiler engineer from SiFive. So here's today's agenda. Today's tutorial talk is intended to serve as a reference for developers and newcomers at Spike. The target of today's tutorial is to be concise and provide a good starting point for Spike, so the whole talk might be shorter than scheduled. I thought of introducing more detailed mechanisms, like how the extension supported is parsed from the arc string provided in the command line. However, I think people should be able to trace into the actual code and learn more about the detailed functionalities, as the code itself might explain better than me. So today, I will focus more on the infrastructure while we still have some code trace, and how an extension like the V extension will be extended upon it. First of all, I will give a brief overview of Spike and its basic usage. Then, extensively, we will go through the main components of Spike by tracing through how to extend the V extension onto Spike. Lastly, we will briefly go through how we can use the interactive debug mode and extend it for our own debugging investigation within Spike. Well, before starting the presentation, I want to thank the following people, because I also learned Spike by myself by tracing through code, but I find that these three from PLCT, they had a very, very rich Chinese material of Spike in a repo that's referenced down below. And through their materials, I've learned Spike and how to develop upon it. So I just want to thank them before this presentation. Okay, well, Spike may be one of the primary entries for newcomers of RISC-V. As people hope to start with a simple program and run it on RISC-V, so I might as well start by showing some of the existing ways we have to compile C source code into a RISC-V executable. Well, for Clang, which you can build from the public LLVM, you can compile them into object code and then use the GCC linker for linkage, or you can just directly use the compile and link with the GCC alone. Well, please note that these two upstream compilers, the extensions that are supported by these two upstream compilers will differ, as LLVM has a looser policy on accepting patches for extensions, and LLVM allows experimental extensions to be implemented into the compiler. Well, on the other hand, GCC has a more strict policy. GCC only allows patches with a ratified spec. So be noted, and please refer to the actual release note of these upstream compilers for your need. Well, Spike use a front-end server to facilitate the communication between the host target and the RISC-V target. Originally, there was a separate RISC-V front-end server project that facilitates this communication. It is responsible for things such as elf loading and the whole ABI stuff. Well, now this front-end server project is merged into Spike repository, and the original repo is archived. Well, program that requires a full-blown OS needs to be compiled with the Linux kernel. For small programs or embedded systems, a proxy kernel would be sufficient. The proxy kernel performs proxy system calls through the host target interface, while this HTIF is facilitated by the front-end server aforementioned. And together, we will be able to simulate the application binary interface and a lightweight application execution environment. With these two combined, you'll be able to execute and simulate a RISC-V program. Now let us look at the main components of Spike simulation. Here are the basic layouts of the systems on the left-hand side. On the right-hand side are the main headers and classes within. Well, first of all, you would see the sim.h. Under sim.h is the class that encapsulates the processors, devices, and memories in the RISC-V machine. Creation of this object is the start of the Spike RISC-V simulation. Well, furthermore, you can see that the header namings are pretty obvious. You'll find the processor class under devices and memories in the RISC-V machine. Creation of this object is the start of the Spike RISC-V simulation. Well, furthermore, you can see that the header namings are pretty obvious. You'll find the processor class under processor.h, the devices under devices.h, and the cache simulation classes under cachesim.h. Well, I'm just listing this out to be helpful for more detailed trace into the repo after this talk, so feel free to trace this on your own. Now, let us go through how the V extension is supported into Spike. The V extension is handled through an additional vector unit onto the processor, just like what we have in the real world. Well, supporting the V extension can be split into several components, and I will cover them one by one, starting from the vector unit, then the microarchitecture configuration through the command line. Next, we will look at how to add an instruction and allow Spike to recognize the encodings. And along the encoding, we will also need to extend the computational logics of the instructions through headers that are separately defined and hooked into the simulator. And lastly, we'll give a brief look at the disassembler. I hope this code is big enough, but well, can people see it since we have, cool. Well, on the left-hand side is the structure of the vector unit, and you can find it under processor.h. Well, I have the file names on the very front of every code segment, so that will be convenient for your code trace. And some data members are omitted in the code segment for clarity. Well, according to the V extension specification, the vector extension adds 32 vector registers and 7 unprivileged CSRs to a base scalar RISC-V ISA. Well, if you're looking at the slide, you might find that there are only 6 CSRs in the structure here. That is because the VCSR is simply a register that maps the value of VXRM and VSSAT into the single register. So that's why there's only 6 registers by the side. Well, please refer to the spec itself for the actual detail and where actually the bits are. Well, I think something worth noting for people that aren't that familiar with the RISC-V vector extension is the V-type register. The V-type register is one of the most important registers in RISC-V vector extension. Well, through the V-type register, the behaviors of a vector instruction will change. And the V-type register would be configured through the vsetVL instruction, right there in bold and underlined. And within the V-type register, there are several values that would configure to change the vector instructions. First of all is the SEW, which stands for the single element width. The SEW value allows you to control the element width operated in the vector instruction. And the second one would be the ELMO, the length multiplier. The ELMO value allows you to have registers grouping to the vector registers. So you can process more elements per instruction, more than using a single vector register. Lastly would be the VMA and VTA value that lets you control the tail elements and mask off elements of a vector instruction. You can find more on the vector specification. The next thing is that let's start the trace through adding the extension. Right now we have the vector unit, and what I find more easily to explain is by starting from the constructor of the Spike processor. And I think that would be a good starting point for me to explain this. Well, under the constructor of the processor class, we can see the main components that a new instruction extension needs to be extended upon. And I'll go through them one by one. Well, first of all, you can see the check for support of the 128-bit integer for the V extension. Well, that is because the arithmetic of data type with a 64-bit element will use type of 128-bit during simulation. Well, you can imagine, like, when you're doing 64-bit saturation arithmetics, you would conveniently use 128-bit data types and just chop them into 64 bits at the end of the computation. And after this check, we come to the first function. The first function would be the parse varc or uarc string function, which would take the microarchitecture configuration for the vector unit. Microarchitecture configurations of the vector extension will be the VLang and ELang. In the 1.0 specification, we have new sub-extensions like ZVE and ZVL, which is responsible for such configuration. Well, Spike was developed along with the development of the vector extension, so the simulator currently does not support configuration of VLang and ELang through the ZVE and ZVL sub-extension. Right now, you can configure them through the varc option. Well, VLength determines the length of the vector register, and ELength determines the largest element supported by the vector unit. The minimum of a RISC-V vector architecture would be a VLength of 32 along with a ELength of 32. And how are these things configured? Under the configure file, there would be the certain line code highlighted here would generate into a config.h header under the build directory when you trigger it. And as you can see, under the header file, the VLength was set to 128 and the ELength is set to 64. And this is identical to specifying the single letter V in the ISA string to the compiler, which would imply ZVE 64D and ZVO 128B. And as aforementioned, you can configure them through the varc option. And after the microarchitecture string parsing, we have the register-based instruction function, which is responsible for declaring the instruction encodings and instruction logics. Well, as you trace into the same function, you can see that there are macros right here. The declare INSN macro, well, it expands the instruction mnemonics and their corresponding encodings defined under encoding.h. As you can see on the right-hand side, they are the encodings of a vector addition with different types of register operands, masked or either unmasked. And in the same function, the computation logics are also hooked into the Spike. Well, under the same make file, you will see that these instruction mnemonics are declared for some are gathered and declared. Well, this These mnemonics in the make file would later generate a inst list.h file header that would be taken into the macro below and expand into the function declarations below. The headers will be used for macro expansion, which declares the function that simulates the instructions. The external functions are defined through the instruction headers. Well, starting from the same make file, the instruction leverages the instruction template. As you can see, there's a sed command right here, and it takes the instruction template.cc, and through the aforementioned mnemonics, you see the instruction mnemonics will replace the name right here into the function that will be realized through that would constitute the declaration for this external function right here that would be expanded by the define INSN macro. And you can see it is including some header right here with the instruction name, with only the instruction name, with this in a separate folder. Yeah, I think this is kind of a pretty good design from Spike that is open for extension on new instructions, and at the same time you won't be adding too much into the infrastructure, and allows you to extend and don't ruin up the code base. And right here we have the instruction computation header, which is simply an addition. And it itself, this would constitute this would let Spike recognize the computation logics of the actual instruction. Well, you can see there are much more complex instructions, maybe like segment load store or other multiply adds. Well, that would come into the same clear logic under the computation logic header. And here you can find it under, here would be the file hierarchy. Okay. Well, furthermore, we can look into the computation logic header of the vector addition. The macro are extended through the vext macros.h header. Well, I won't try to go deeper here because there will be multiple layers of macro resolution to finally we know what actually is the code that implements it. But I'm introducing Spike and how to extend it right now, so I won't go into that much of a detailed code trace. Well, be noted that you can directly use these kinds of operand mnemonics inside the computation header, which is VD, VS1, and VS2. This is because the correct data type is loaded from the register through the layers of macro extension, macro resolution. I won't be introducing it here, but I think it would be a good practice after this talk to trace through the code behind and see how it does. Well, feel free to do so after this talk. Lastly, we will look at how instruction disassembling is declared through the constructor of the disassembler object. Well, first of all, these are the utilities when disassembling a vector instruction. On the left-hand side, you can see the decoding of a vector instruction, and its decoding of masking, immediate value, and vector registers. On the right-hand side are the vector register names. They're declared under regname.cc. Inside the constructor of the disassembler object, the instructions are registered into the object based on the ISA string provided to Spike. Well, we are going through multiple levels of macro here. First of all, you will see the define vector VV and define vector Vx. They will be macros that would call to the function that registers the vector instruction disassembling. Well, similar macros of these are defined based on different types of register operands. Then below, for the above macro will be collected into the second layer, which is this disasm op IV Vx. That would mean that this instruction specifically, it would only have mnemonics of VV and VX. And this macro is a macro that collects multiple calls of these instruction disassembling registration functions. As an example, you would see that the vector integer minimum instruction is this kind of macro, uses this kind of macro. And in the below, you can see how the add vector instruction function works. The argument classes, which are the operands right here, are passed into the disasm insn object constructor. And that is the object that would be bookkeeping the disassembling of that specific instruction. Pardon? And that is all you have to do to support the vector extension in Spike. And here is a recap of the bullet points we have went through, and you are able to trace the full actual pull request in the references listed below. They are submitted by Jimin Zhimin Zhao from SiFive and reviewed within SiFive and submitted into Spike. Well, lastly, let us go through some tips through interactive debugging. Well, Spike itself also allows hooks for you to extend functionalities for interactive debugging. As an example, since we have just introduced how to extend the V extension into Spike, so let's see how we're going to add a functionality that dumps all the vector registers into Spike when interactive debug mode. Well, it is only a simple three-step approach. First of all, you have to add a helper under interactive CC. Next, under the main interactive function, you would need to register your helper into the funcs hash map. That would be the desired string you would use when you are interactive debugging. And lastly, you just have to add it into the command line description so people can know. Yep. And I don't think that add helper would be a big deal of problem right here. I'm not showing too much code because the vector register itself, you just have to go into the vector unit and you have the vector register names, just list them all through printf. So that won't be a big deal here, and that's the overall 3 steps to add the interactive debugging. And a quick start would be to add the -d when executing Spike. That would help you to trigger the interactive debug mode. You can use help to see what command you have, but basically, if you know how to use a debugger, that's all it needs to start a debugging, and you know how to do a debugger. Okay. Let's have a quick recap on today's tutorial. Today, we went through the overview of Spike. Then we covered the parts of code that would be needed when we are extending the V extension onto Spike. And lastly, we briefly covered how to extend interactive debugging in Spike. Okay, and that's the end of today's presentation. Well, we have plenty of time left, so we're open for questions. Well, I'll be here for the whole hour, so you can just ask me personally if you want to. And that's all.